Okay, so the next section is 2.2. We're looking at the derivatives of polynomial functions. So far we have understood what are derivatives. Is basically the difference quotient with the limit of h approaching 0. What is the rate of change over two very close points, or at one point with another point that's very close to it. Now, how do we apply the derivative of various types of polynomial functions? We're going to take a look at that now. So f at x equals 3. This is a constant function. It's f at x is equal to 3. So the slope or the rate of change will always be 3 because, it's going to be 0 because if you look at this graph, it will be y is equal to 3 and it will be a straight line going across, which means it has no rate of change. It's not going up and it's not going down. So the derivative or the rate of change of a constant function, and we write the derivative as f prime at x, the derivative of a constant function, meaning there's no variables inside, will be 0 because it doesn't change. It doesn't go up or down. It has a rise of 0 and a run of whatever you want to come up with, but it does not rise at or run, it doesn't rise at all, therefore it has a rate of change of 0. Let's look at another example. Now we have f at x is equal to 3 to the 3 times x. In this situation, it's another one where very straightforward. If you were to graph f at x equals 3x, it would be a simple line with a slope of 3, which means the rate of change is always going to be 3. So the derivative function for a linear equation will be just 3. I mean, the slope of the tangent to a straight line is the line itself. Therefore, the derivative would just be the slope, and in this case, it's going to be 3. What we're going to look at now is the third example. This is a parabola. The rate of change of this function is varying, is dynamic. It keeps on changing depending on the x values. Therefore, there is no one specific value that we would get, like we did in a horizontal line or a linear function. When we're dealing with the rate of change of or the derivative of a quadratic or above for polynomial functions, we're going to do a little trick. Okay, I'm just going to write this down here. F at x is 3x squared. The derivative, we're going to take the exponent, bring it down, and multiply it by the coefficient. So 3 times 2. So it's going to be 3x is here. So we're going to multiply it by 2. And we're going to subtract 1 in the exponent. So 2 minus 1 is just a 1. So what this turns into, 2 times 3 is 6x. So the derivative here would be 2 times 3, which is 6, and x. We can actually apply the same logic here. The derivative, the exponent here is 1. So 1 times 3 is 3. And then when you subtract 1, it becomes a 0. X to the power of 0 becomes 1. So it's the same thing as 3 multiplied by 1. So again, the key to understanding the derivative function of using a polynomial function is going to be something called the power rule. And the power rule is that you would multiply the exponent with the coefficient and simply subtract 1 to find out what the derivative is. We're going to look at a few examples together, and we're going to look at certain different ways that the derivative can be applied, inshallah. Let's look at a few more examples. Applying the same rule to f at x is equal to 12 times x to the power of 4 over 3. So once again, the exponent comes down and is multiplied with the coefficient. So it becomes 4 over 3 multiplied by 12, and then x, and then we subtract 1. So 4 over 3 minus 1 would turn into 4 over 3 minus 3 over 3. That turns into 1 over 3. Simplify this, 3 and the 12 simplified before, because 12 divided by 3 is 4. 4 times 4 is 16, x to the power of 1 over 3. this represents the derivative or the equation of the instantaneous rate of change of this function at any given point. Let's do this again here. We have our function. Should write that down. The derivative. When you have subtraction, you are going to treat it as if it's two separate functions. This is the sum rule. This is where you have different, if a function is composed of multiple terms being added or subtracted, find the derivative on their own, right? You don't need to combine it in any way. So we're going to find the derivative of this. 2 times 3 is 6, and then 2 minus 1 is x to the power of 1. X, the square root of x is the same thing as, it's going to be x to the power of a half. So this would be minus, and then 5 times a half would be 5 over 2, or 2.5. And then 1 over 2 minus 1 would give me x to the power of negative 1 over 2. All right. The trick here was we have to remember that the square root of x is the same thing as x to the power of a half. So the exponent, we bring it down and multiply with a 5. So 5 times a half would be 5 divided by 2. And then we subtract the 1 from the exponent. So 1 over 2 minus 1 will give me negative 1 over 2. If I want to simplify this, this is perfectly fine as a solution, but if you want to, you can do 6x minus 5 over 2 root x. And for the last one, in a question like this, we have 3x plus 2. However, the exponent is being applied to the entirety of 3x plus 2. So we can't treat it the same way as this. What we'll have to do now is expand it into a polynomial form that we can differentiate, that we can find the derivative of. Because as it is right now, we cannot. So f at x, we expand this using distributive property, and we get 9x squared plus 12x plus 4, and then we can find the derivative, which would then be 9 times 2 is 18, x, 2 minus 1. 12 and x, right? This would be the x has a exponent of 1. 1 times 2 is 12, and then the x becomes x to the power of 0. And what is the derivative of a constant? 0. You don't have to write that. I'm only writing it there to show you that that's what's going to happen. And if I want to simplify this, it's 18x plus 12. Because what is x to the power of 0? It would be 1. So 12 multiplied by 1, or any number multiplied by the 1, would be that number itself. Right? What I want to expand on a little bit more is, how do you write these in Leibniz notation? Your process is essentially the same. The derivative function essentially is the same thing as dy over dx. So for this one, right, so if we look at for part B, do it again, it's y is equal to 12x to the power of 4 over 3, and the derivative of dy over dx would then become 16x to the power of 1 over 3. There is no difference right now, because the derivative is just, you find the derivative of this function with respect to x, meaning you leave x in there. X does not change, you change everything else around it.